As I mentioned last week, last video, we talked about that this equation is related to Navier-Stokes equation, and then the Navier-Stokes equation is actually by far this whole piece of equation over here. Okay, but we didn't thought on how to derive that, so we can straight away use this equation. That's all. I'm not gonna derive it, but you can see that there are some relationship with that. Okay, it takes on a certain similar relationship. So what we do is actually to let you know and get a feel of what is the equation itself. So the equation itself is mostly on Newton per meter cube. So it's the force over a certain volume. And it's a very chim to understand thing, I also don't know. So similarly, this is also Newton per meter cube over here. And then we have a rate of change. So we're talking about this equation. It's the same as this portion over here. Except we are doing with velocity now. It's not density. Okay, so if you were to compare, this one is partial rho, while rho is outside now, this is partial u. So there's a little difference in there as you can see. So similarly to here also. So you have a partial u, and then there's a u outside. Nonetheless, you have a rho. So yeah, let's go through the definitions. So this is the density. This is the rate of change of the x component of velocity initial. So this is when you're at, I believe is at the initial point. Okay, when time is 0, it is actually at velocity u. And then when time increases, the rest comes in. Okay, the rest comes in, so you move in some direction over here, maybe here, whatsoever. Okay, so x, y, z direction all comes in. So at first, when t equals to 0 is at this point, and then when time start to roll, you have certain movement. So you may at this point, you may be at this point, you may at this point based on velocity of the u, v, and w. That's what it is. And then the rate of change for x component of velocity is simply saying the acceleration of the particle. The rate of change of the velocity is actually acceleration, right? Sorry, meter square is the velocity, while rate of change is just multiplying with 1 over s. So similarly, this portion over here is the rate of change of the position of particle in velocity field. It's the same thing, rate of change of the position of the particle. So so you have a meter square. Okay, so I'm just gonna derive the SI unit. So u is actually meter square, right? This is this u over here. So meter square divided by, sorry, hold on, yeah. So again, sorry, my pen is not working. So meter square multiply by meter square. This is the meter square over here divided by meter, right? So you will have 1 over s in this case. So it's velocity multiplied by 1 over s. So this is how you derive saying that this is acceleration. And then for pressure gradient, okay, so now we are talking about pressure gradient. So since I can prove you to this, therefore this and these are the same as this, right? They are the same configuration, so they are come together. So it's the rate of change of the position of the particle. The particle move over time. Okay, so let me repeat again. So at first, when time t equals to 0, you have particle over here with certain velocity. When time starts to roll, maybe 1 second, 2 seconds, or 3 seconds, in one possibility that this particle may be here, another possibility is that this particle may be here, or maybe here, based on u, v, and w. Okay, so this is what it is, and also based on density lah, And then for pressure gradient is the pressure is the hold on. So you have a velocity profile over here, okay, and then the pressure gradient is actually, because if you were to remember Bernoulli equation, the higher the pressure, the lower the velocity. Okay, if you don't remember, it's okay. So you just need to take note that the higher the pressure, the lower the velocity. Nonetheless, if the higher the velocity, the lower the pressure. So in this case, the velocity is high over here, this point. So the lower the so if you were to compare this point to this point, the velocity over here is much faster than this. So therefore the pressure itself is lower than this point, right? So what I mean is I managed to squeeze out an equation. This is the Bernoulli's equation. Okay, imagine we ignore this rho gh because this is a very small distance. So the h does not apply, much into the, system. So we can actually eventually ignore this. Okay, while the rho itself, it's the density of the fluid, and the density of the fluid it's not that much. So because it's kg, while this is just maybe this is just a thin layer of oil. So therefore we can actually say this is cancelled. So as you can see, the rest is actually pressure plus half rho v square. Okay, so the velocity increases, okay, because it is equals to some constant, right? So maybe I should bring this thing out over here, right? So we are talking about some constant. So maybe I call it maybe some values. I put it um 8. So let's say if you have a certain velocity which is maybe this term itself, okay, maybe this term is 6. So therefore p is equals to 2, right? So if your velocity is high, your pressure will be less. So while your velocity is lower, so let's say if this now is actually 1, the pressure is actually 7, right? So the velocity in this case is actually the largest, right? So therefore the pressure itself is kinda pretty much very low, right? And then when it increases, and then when the velocity decreases, the pressure actually increase, right? The pressure actually increase. So therefore so at this point maybe I should draw it now. The pressure, maybe we have another graph. Okay, so this is the pressure. So as the velocity increases, the pressure decrease. So maybe at velocity is max, okay, the pressure is actually 0. Okay, the pressure is we assume is 0. Maybe we say that the velocity is extremely large, that the pressure itself is negligible, so this is 0. And then when it slowly decreases up to this point, the velocity becomes maybe like 6, and then the pressure increases to 2, right? Because 2 plus 6 equals to 8. I just take any constant and let's do it. So therefore, the pressure will actually increase to 2, right? And then as you go down again, you go down more, the velocity actually decreases. Okay, this is like 4 and this is 4. So you have, and then when it all goes down all the way, you have some scale. I may be wrong that this may be not be linear. This is not linear. Okay, this is not linear. I may be wrong, but yeah. Given that this velocity profile is this curve, so I think the pressure itself may be some square root curve, which is like a square root graph over here like that. So it's like a little opposite from the velocity profile. Okay, if you were to compare, right? So this one is going down and this one is going up. So as you can see, the gradient itself is actually increasing as the velocity decreases. So yeah. So actually, later in the later videos, we'll talk about why this velocity profile is associated with a negative gradient. Okay, it's associated with a negative gradient. The reason why is because we are talking about the distance y as y increases. Okay, when the y-axis increases to up to this point, right? So as the y increases, the velocity increases, right? So as the velocity increases, the pressure should be decreasing, right? So instead, the graph should be in this form. So at first, the pressure should be very high, and then when velocity starts to increase, this one should start to go down. So there will be a negative, going down negative gradient. So previously this one is actually positive gradient, right? So I hope I didn't confuse you anything. And then yeah, so let's get back to the pressure gradient. You just get a feel of it. I talk a lot of it. Dynamic viscosity is actually this mu over here. Okay, it describes the viscosity when it is moving. Okay, when it's moving, the viscosity may change a little. I don't know, but this is what it means. And then stress. When you see dynamic viscosity mu, you'll know that this is stress. Okay, if you remember the very first chapter, this equals to force over area. This is the stress, shear stress. This is the shear force, and this is the area. So this is what it is. And then this portion over here is just some terms. So the unit over here for the dynamic viscosity is actually this. Okay, while the unit over here for this is actually this. And just let you know, partial square u is actually the SI unit is actually meter per second only. Okay, it's meter per second because the partial square is outside of the u. If it's like this, then it is like meter square per second square. But since it is this, then it is square over here, and then divided by y square, which is meter square, right? Because this is y meter square. I hope you get what I mean. So therefore, if you divide, you get 1 over Sm. How do I get so? I just cancel away this, and then maybe I should let you see in a more clearer view. Divided by 1 over meter square. Okay, right? Divide on the meter square equals to meter per second times 1 over cancel, you get 1 over Sm. So I have this over here. So this is all it is. And then for this part is the force. This force is a Newton per meter cube force. Okay, I don't know what the hell. Then know that this force is acting on the fluid element to produce an acceleration of the element in x direction. So as you can see, this whole equation is actually to describe the element itself, particle itself. This describes the acceleration needed to actually accelerate the particle, and then equals to, so to redefine this equation, it can also be redefined as the pressure gradient multiplied by the amount of stress within the fluid on the fluid itself, and then plus a certain forces, maybe some external forces pushing it, accelerating it. So this is just a very brief concept of the Navier-Stokes equation whole thing. Yeah. So in y and z direction, they are also the same. I'm just taking the u out. Okay, so simply say this is the template for subbing in. You can see if you were to compare, right? The u is gone. Okay, all the u's are gone. Okay. So on the top, if you are talking about x-axis, you sub in the numerator as u. In this case, you see is v. In y direction is v, and in z direction is w, w, w. As you can see. So this one also, so you just fill in the blank. So this is just a template for you to know which are the things to sub in, and then the rest are actually the constants one. So this settles down the Navier-Stokes equation for the Cartesian coordinates. We're talking about x, y, and z. So just to give you a quick preview, for non-pipe system, okay, which is what we are gonna do next, is actually using Cartesian coordinates, which is this equation over here, and then apply boundary conditions to solve for constants. Later I'll talk about it. And then for pipe system, you have to use polar coordinates. Okay, radius r. So just to let you know, non-pipe system you use Cartesian. For pipe you use polar coordinate. So previously I promised I start to do a question, but yeah, apparently we are actually doing the question. I'm defining the equation now. So next video we'll talk about the assumptions, and we can start to do the question itself. So I'll see you in the next video.